The Perm model is a parametric representation for 3D human hair, aimed at enhancing various hair-related applications. Unlike previous models, Perm disentangles the global hair shape and local strand details using a PCA-based strand representation in the frequency domain. This allows for more precise editing and output control. The model leverages a strand representation to fit and decompose hair geometry textures into low to high frequency hair structures, which are then parameterized with different generative models. These generative models emulate common stages in the hair modeling process. The Perm model is composed of two parameter spaces, theta and beta, which control the global hair shape and local strand details, respectively. The theta space represents guide strands that capture the overall shape of the hair, while the beta space represents wisps that capture local details such as curliness. The authors conduct extensive experiments to validate the architecture design of Perm and deploy the trained model as a generic prior to solve task-agnostic problems. The results demonstrate the flexibility and superiority of Perm in tasks such as 3D hair parameterization, hairstyle interpolation, single-view hair reconstruction, and hair-conditioned image generation. The Perm model is designed to address the biscale nature of hair, where hairstyles with similar global shapes may exhibit variations in local details. By disentangling the global hair shape and local strand details, Perm enables more precise control over hair modeling and facilitates a range of applications. The authors provide their code and data publicly available, allowing for further research and development in the field of hair modeling. Perm is a parametric model of 3D human hair, designed to serve as an effective prior for various hair-related applications. Formulated as m, theta, beta, r, it is conditioned on three key parameters. Theta, the guide strand parameter for global shape. Beta, the hair styling parameter for local details. And r, a predefined root set for hair density. The authors introduce a novel strand representation based on principal component analysis, PCA, in the frequency domain, which effectively captures the nearly periodic behavior of hair strands. This representation enables independent control of global shape and local details, providing a high degree of flexibility and customization. To train Perm, the authors employ a multimodal approach, combining style GON2 for guide textures, a variational autoencoder, VAE, for residual textures, and AUNet for super resolution. This approach allows Perm to generate highly realistic and detailed hair models. The authors demonstrate Perm's capabilities across multiple applications, including 3D hair parameterization, hairstyle interpolation, and single-view hair reconstruction. In each of these tasks, Perm achieves performance equivalent or superior to state-of-the-art task-specific alternatives, showcasing its versatility and effectiveness as a prior model for hair-related applications. The Perm system is a parametric representation for multi-style 3D hair modeling that leverages a guide strand function g, theta, to synthesize guide texture tguide and guide mask mguide. These are then super-resolved with function f, to obtain upsampled texture tlau. The high-frequency part is handled by a hair styling function d, beta, which maps parameter beta to residual texture trays. The two textures are concatenated to form geometry texture T, which can be sampled and decoded with function S, to obtain strand geometry. Unlike existing approaches that rely on volumetric fields, the Perm system is better suited for curly and kinky hair. It relates to Grün Gen, which constructed hierarchical hair latent spaces represented in the scalp texture space, but offers independent control over global hair shape and local strand details through its hybrid hierarchical parametric hair representation. This approach has applications in various fields, including human digitalization, 3D facial expressions, whole body reconstruction, and animal modeling. The authors introduce a novel hair modeling architecture, Perm, which leverages a PCA-based strand representation in the frequency domain. This representation enables the smoothing of hairstyles by truncating the strand PCA coefficients, as shown in Figure 4. The Perm architecture is illustrated in Figure 3, mimicking the current hair modeling pipeline in industrial software like XGen. It consists of several components, including a strand mapping function S, a guide strand function G, a super resolution function F, and a hair styling function D, parameterized by controlling parameters theta and beta, respectively. The Perm model can be expressed as equation 1, where sample denotes nearest neighbor interpolation, and phi specifies the full set of trainable parameters. Novel 3D hairstyles can be synthesized by varying theta and beta, while the hair density can be adjusted by manipulating the number of roots in R. The authors delve into the details of the strand parameterization, which is inspired by the nearly periodic behavior of hair strands. They define a low-dimensional parameter space based on PCA in the frequency domain, as shown in equation 2. This formulation enables the representation of 3D strands as a vector of linear coefficients gamma. The authors compute the mean phase vector S and principal components X by applying the discrete Fourier transform, DFT, to all strands in their collected hair models and performing PCA on the computed Fourier bases. They set the number of PCA coefficients, gamma, equals 64, which explains almost 100% of the variance in the training set. This PCA-based strand representation differs from previous work that uses a VAE to learn the strand latent space. The authors claim that their formulation attains comparable or superior performance while reducing training time and GPU memory consumption due to its analytical computation. The Perm method introduces a novel parametric representation for multi-style 3D hair modeling, leveraging principal component analysis, PCA, to decompose strand geometry into low-rank and high-rank portions. The first 10 PCA coefficients capture the rough shape of each strand, while the remaining 54 coefficients encode high-frequency details such as strand curliness. This decomposition forms an explainable parameter space, allowing for effortless smoothing of a given hairstyle by truncating its strand PCA coefficients or creating diverse styles by blending the low-rank and high-rank portions of PCA coefficients from different hairstyles. The authors also introduce a 2D parameterization of hairstyles on the scalp surface as a regular texture map, referred to as a hair geometry texture, which is downsampled to 32 by 32 to represent guide strands. A separate neural network is employed for guide strand synthesis, aligning with existing hair modeling stages, including guide strand synthesis, guide interpolation, and hairstyling. The training objective is identical to style GAN2, consisting of a non-saturating GAN loss with R1 regularization on both the texture and mask. This approach facilitates hair reconstruction either from 3D strands or 2D orientation images. The paper discusses the development of a novel method for generating realistic hair textures in computer graphics, leveraging the capabilities of deep learning techniques. This method, named Perm, aims to create high-quality hair models by employing style GAN2 to synthesize guide strands and a VAE-based network to generate residual textures. The authors first introduce a PCA-based strand representation, which significantly reduces the number of parameters required compared to strand VAEs trained in the spatial or frequency domain. This representation demonstrates a remarkably small position error and effectively preserves strand curvatures. In the guide strand synthesis section, the authors compare the performance of style GAN2 with a PCA-based representation. Quantitative results show that style GAN2 learns a more expressive latent space than PCA, resulting in smaller position and curvature errors. This is attributed to the limited number of samples available for guide textures, leading to a higher compression rate and poorer performance of PCA. The paper also explores different interpolation methods for upscaling guide strands, with nearest neighbor interpolation producing aliased strands and linear interpolation providing smoother results. The authors conclude that Perm can generate realistic hair models with high-quality textures, offering a promising approach for future research in computer graphics and machine learning. The authors compare their PCA-based strand representation with other VAE-based representations and a simpler PCA-based formulation in the spatial domain, demonstrating that their method achieves the most natural results, resembling guide strands and forming reasonable hair partitions. They discuss issues with style GAN2 in synthesizing guide strands and propose a VAE-based architecture for higher reconstruction fidelity. Quantitative comparisons with Grumgen's VAE-based strand representation show their method achieves better reconstruction with slightly higher curvature errors. The authors also report smaller position and curvature errors by embedding hair geometry textures into the latent spaces. Finally, they showcase the application of Perm as a generic hair prior for solving different downstream tasks. The guide strand's nearest bilinear U-net is applied for 3D hair parameterization, utilizing differentiable optimization to fit Perm parameters to target 3D hair models. This capability is demonstrated in Fig. 9, showcasing the model's ability to generate reasonable guide strands even for hair models lacking them. In addition, the section explores hairstyle interpolation, illustrating the capacity to edit hairstyles with varying granularity by interpolating corresponding parameters. This is exemplified in Fig. 10, which displays linear interpolation of guide strand and styling parameters. Finally, the section discusses single-view hair reconstruction, where Perm parameters are optimized to minimize the energy of generated hair when projected to 2D images. The results are compared with HairStep, highlighting better preservation of local details and global shape. The paper introduces a novel parametric representation for multi-styled 3D hair modeling, known as Perm. This representation enables the creation of diverse hairstyles by interpolating between different parameters. Figures 9 and 10 showcase the versatility of Perm in fitting various 3D hair models and interpolating between them with different levels of granularity. The methodology draws inspiration from previous works in morphable models, such as Bland's and Vetter's 3D face synthesis, and facial expression databases like Face Warehouse. The paper highlights the significance of Perm in expanding the possibilities for 3D hair modeling and styling, while also acknowledging the need for further research to overcome current limitations. In a qualitative comparison, the proposed method is evaluated against HairStep, Zhang et al. 2023. For single-view hair reconstruction, as illustrated in Figure 11. The results unequivocally demonstrate the superiority of the proposed approach in generating more realistic and detailed hair structures. Notably, the proposed method excels in capturing intricate hair details, such as strand texture and wisps, which are often missing in HairStep reconstructions. This is attributed to the proposed method's ability to leverage both local and global cues, enabling a more comprehensive understanding of hair geometry and appearance. In contrast, HairStep relies heavily on local features, resulting in less realistic and less detailed hair structures. The proposed method's improved performance is further supported by the visualizations in Figure 11, which showcase the method's ability to reconstruct complex hairstyles and hair textures. The comparison also highlights the proposed method's robustness to varying hair lengths, styles, and lighting conditions. This is achieved through the incorporation of a hierarchical feature extraction module, which effectively captures hair features at multiple scales. The results collectively underscore the proposed method's potential in advancing the state-of-the-art in single-view hair reconstruction, paving the way for applications in computer vision, graphics, and virtual try-on. The research papers discussed in this summary focus on the development of 3D hair modeling and capture techniques from various angles. They begin with a parametric representation for multi-style 3D hair modeling, followed by the capture of hair geometry from multiple images. The discussion then moves to expressive body capture, including 3D hands, face, and body from a single image, and continues with encoding in style for image-to-image translation. Significant findings include neural strands for learning hair geometry and appearance, as well as CT2 hair for high-fidelity 3D hair modeling using computed tomography. A local appearance model for volumetric capture of diverse hairstyles is also highlighted, along with HVH for learning a hybrid neural volumetric representation. Lastly, mono hair is introduced as a method for high-fidelity hair modeling from a monocular video. These papers demonstrate the advancements in 3D hair modeling and capture, offering insights into the techniques and methodologies used to achieve high-fidelity representations of hair and body from different perspectives.